Hello, I've got a fun one today. We're going to skip ahead a bit to molecular kinetic theory model. It's 3.6.2.3. It's basically like the tricky bit of thermal physics. And you can see there's a lot of blank space because I'm going to try and do this derivation in one take because I cannot be bothered to edit these videos, no matter how easy you think it might be. I just can't be bothered. We'll start off with the bit of easy bit. So Brownian motion, Robert Brown put pollen grains in water. Notice they jiggle about. The same thing can be mimicked with smoke. Obviously the smoke is only jiggling around because it is being bumped into by much faster moving atoms of air or water. And this was evidence of atoms. It's Brownian motion. Brown didn't know what was causing this. It was Einstein that came along and explained it later on. But, he still gets his name there. So there you go. Brownian motion is evidence of atoms. Then in the previous section, it's PV is nRT, which is an empirical formula. So PV is nRT. The physicists that discovered PV is constant. Then P over T is constant. And then V over T is constant. This one was Boyles's law, and this one was Charles's law here. So Boyles's law and Charles's law. Now they came together and created PV as nRT from all these laws, where N is the number of moles, R is the ideal gas constant. But these also can be explained in terms of kinetic theory, which is a theoretical. So you're kind of thinking about what would happen and coming up with equations based on the theory of it. Now, the pressure is about the number of times the gas molecules are colliding with the container and the force with which they are colliding. So this one shows us that if we increase the temperature, the pressure is also going to increase because they're going to collide more often with the walls of the container and with a greater force, and pressure is force over area. Pressure times volume is a constant. If we keep the temperature the same, if we increase the volume of a container, the pressure is going to decrease, because at the same speed of motions, if you give it a much greater area, you're going to have a lower pressure because the particles are just not going to hit it so much, and vice versa. Pressure, volume and temperature. So if pressure is kept constant, you increase the temperature, the volume also has to increase. You can't increase the temperature and keep the pressure constant without an increase in volume. So we can kind of explain all of these theoretically, and then this is what all this equations comes from. We're thinking about theoretically a particle hitting a wall and all the stuff that comes from that. Now, for an internal gas, the internal energy of the ideal gas, the internal energy of an ideal gas is equal to the kinetic energy of the atoms, which is half mv squared. Now, this becomes tricky because when we talk about the average velocity of a particle, if you have a gas with, a insane number of particles in it, Avogadro's numbers of particles in it, what you're going to have is a range of different speeds, right? And if you do chemistry, there's more on this. A level chemistry goes into this in more detail. We just know that there's going to be a range of speeds. You're going to have some particles moving much faster than others, but there's also going to be kind of like an average speed. Now, we're not really interested in the average speed for this. We're interested in the speed of a particle at average temperature, because it's the temperature of the particles that we're looking at. And because the temperature is proportional to the internal energy, which is proportional to the kinetic energy, which is proportional to v squared, we don't really want the average velocity or the average speed of a particle, because that would give us the average speed, but not the average speed of a particle of average temperature. So there's this quantity called root mean square speed. Now, a lot of why we use root mean square speed doesn't come up, that it's just kind of presented as a fact. Now for this bit we're using root mean square speed, and you don't have to, as far as I'm aware, it's not come up yet that you have to understand why it's root mean square speed. So I guess don't worry about it. Trust me, it's root mean square speed for this bit. Now, the root mean square speed is done, say you take the three speeds. First of all, you square the speeds, so you get 4 plus 64 plus 4, if these are your original speeds. Then you find the mean of the square speeds, so you divide that value by 3, because there were 3 of them, and that's the mean, and then you root it. And that gives you the root mean square speed, and like I say, it's the speed of a particle of average temperature. So that's kind of what we use going forward when we're talking about speed. So kind of instead of EK is half mv squared, we would actually say, well, the kinetic energy of a gas will be a half mass times the root mean square speed, right? That's the kinetic energy of average molecular kinetic energy. It's going to be the root mean square speed instead of just v, because taking into account there's a range of gases. So you can see we end up squaring it anyway, but the point important is that we found the average square speed and then we rooted it, so we've got a quantity with the same units as velocity. Right. So now this is the messy derivation that you have to know how to do. This is what you're getting at. I mean, good news is you get given this equation, so you know that if you have to derive it, that's where you're aiming for. These are the three equations that you need along the way, really, and a few other kind of assumptions. So you need velocity is, speed is distance divided by time, force is the rate of change of momentum, and pressure is force over area. And it's about remembering what you need, I guess, and then trying to get there in the exam if they ask you to derive it or part of it. Now, the kind of setup we have is weird because this is a theoretical thing. So we're imagining we've got a particle with velocity in the x direction only. It travels the length of a box. It hits the side here with an area A, and then it travels back in the other direction. So it applies force on the box and therefore pressure, right? And this is how we're going to get there. Now, first of all, we think about the time that it takes for the box, the particle to go there and back. It's obviously going to go there and back in the same direction because it only has Vx. So I've kind of done the dashed line above. So speed is distance over time, so time is distance over speed. So the time that it takes for the particle to travel the length of the box and then back again after its collision with the wall is going to be twice the length divided by the speed it has in the x direction, right? Then we're going to look at the next equation, so the force. So what force did it exert on the particle, exert on the wall in that time? So the force is equal to the rate of change in momentum of the particle divided by the time taken for that change. Now, the rate of change in momentum for the particle, because it's hitting a wall and then bouncing back, on the way here, its momentum is mass times velocity. Then it travels in the opposite direction and its momentum then becomes minus mass times velocity. So the rate of change in momentum of a particle hitting a wall and rebounding is actually 2 mvx, because the rate of change, the change in momentum is going to be the final minus the initial. Yeah? So it's going to be mvx minus mvx, or 2 mvx. We need that. That 2 is going to cancel out a bit later on, actually, with that 2 there. So the force is going to equal to twice mvx divided by the time taken, which is this, 2 times the length divided by vx. Now, because I'm dividing by that, I'm actually going to multiply the top by it. So the force becomes 2 mvx squared divided by 2l, and those 2 cancel, so I just get force is mvx squared, so the velocity in the x direction squared, divided by the length of the box. Beautiful. Now my next equation, so the pressure that it applies. Pressure is force over area. Pressure is equal to force divided by area. This is the force, so I can turn the force into pressure. I mean, there's no force in this equation, so I'm going to have to get rid of it. Pressure is force over area, so I divide this whole lot by area, so I get this equation here. Pressure is equal to mv, velocity in the x direction squared, divided by the length, and now I'm timesing that by the area. And surprise, surprise, the length of a box times the area of a box gives you the volume, right? Length times area is volume. Volume is equal to length times area. So the pressure is going to be equal to mass of the particle times the velocity in the x direction divided by the volume. Now that's pretty decent, yeah? And you can see I've got all the kind of stuff that I want there. And the next 2 things are just kind of like thinking about getting what we're only talking about a particle moving the x direction here, and then thinking about the fact that we've got like loads of particles in this box. The loads of the particles in this box I think is the easiest one to deal with. Straight away I'm just going to say, well, actually it's not just one particle, it's n numbers of particles. So n is the number of molecules, so the pressure is going to be equal to the number of molecules, if we're trying to scale it up, Vx squared divided by the volume. So we're getting there. Now, this Vx squared disappears because the root mean square speed, which I kind of spoke about over here, the root mean square speed squared is going to be equal, the particles, if we've multiplied it by n number of particles, we're going to have particles moving in the x, the y, and the z. So the root mean square speed is going to be equal to the particles moving in the x direction squared, plus all the particles in the y direction squared, plus all the particles in the z direction squared. Now, so, you know, all 3D directions they could be moving in. Now, if we assume it's average distribution and it's going to be equal numbers of particles moving x, y, z, which is a fair assumption to make because there's so many of them, right? So there's going to be about a third moving in each direction. So these are essentially all the same values, right? So Vx squared is going to be the same as Vy squared, which is going to be the same as Vz squared because there's so many particles with this distribution of speeds. So the root mean square speed squared is going to be equal to 3 times the velocity in the x direction squared. And that's where this nice third comes from. So therefore a third CRMS squared is going to be equal to the velocity in the x direction squared. And then we just sub that back into that one and we get PV is equal to a third NM CRMS squared, which is what we were trying to derive. And you've got to know the equations that are used. It's called an algebraic approach and it involves conservation of momentum. So this is the idea of conservation of momentum, that the change in momentum is twice the original momentum. Now, this then goes a bit further and there's some equations for the average molecular kinetic energy. Now, you don't have to know where they come from, but the average molecular kinetic energy, which is this, right, a half m CRMS squared, we can manipulate this equation and PV is nRT. And then essentially if you put a half in here, you get 2/3 n, a half m CRMS squared. Right, so I would put PV is 2/3 NM, a half CRMS squared. And so then you get 3/2 PV over NM. Now, if you plug in PV as nRT, you get 3/2 nRT over NM is equal to this. Now, N, number of moles divided by number of molecules, is 1 over Avogadro's number. N over N is going to be Na, number of Avogadro's molecules. But like I say, we're not going to worry about this because this is not a derivation you need to know. That's the derivation you need to know. This is an equation that gives you the value for the average molecular kinetic energy by combining those and those, and it's given. You just have to use this equation. 3/2 K, that's the Boltzmann's constant on the data sheet, times the temperature of a gas. Because this is the kinetic energy, it's going to be proportional to the temperature of the gas. And that's the same as 3/2 R over NA times the temperature. Because the Boltzmann's constant is really just the ideal gas constant, multiply the number of Avogadro's number. Now, Boltzmann constant is ideal divided by Avogadro's number, right? And that's why there's another version of PV is NKT as well. So that's it. It's a lot, I know. I'm happy to go through it again. If it didn't help, let me know. Good luck.